In this lecture, we're going to look in more detail at polar reactions under basic conditions. So what I want to do is start with the common bases that we'll see. So a pretty popular one is KOT butoxide. And so this is potassium tert butoxide. In organic chemistry 1, we labeled this as an E2 base. So the way this works is we have a potassium cation countering an oxygen anion that's attached to a tert butyl group. So the tert butyl group is this thing that sort of looks like a chicken foot. We label that TBU. There's a few ways to write TBU. I think we went over that in the first lecture of the course. The TBU provides a lot of steric hindrance. So I'm going to call this sterically hindered. Nobody in my career has suggested that sterically is not a word yet, although I'm not convinced that it is. Anyway, so it's a sterically hindered base, alkoxide base. And so what this means is that since it's sterically hindered, it's rarely going to do nucleophilic addition. Only in the case when the electrophile is sufficiently unhindered. Okay, so that's one base that we'll see a lot of, and we'll see things like it, but potassium tert butoxide is probably a favorite among the chemists. The other one is NaH, which is sodium hydride. When you buy sodium hydride, you typically buy it as a 60% sort of solid solution. So it's a solid, and you just know that it's about 60% pure of solid, and then the rest is mineral oil. And that just helps to protect it against moisture in the air. But if we break this down, we see that we have sodium, which we label as Na+, adducted to something else. And there's probably a bit more of covalent character in this bond, but we can think about it as having an H-. Now, H-, that implies we have to add the IDE suffix to whatever is negatively charged. In this case, it's hydrogen. So this is a hydride. And that's where the name sodium hydride comes from. And how this looks, if you want to do a formal charge calculation, you would say it has a lone pair of electrons. So its formal charge is then, I'm going to label this as a lone pair. And I'm going to draw an arrow instead of a colon, just because it gets a little confusing. Okay, so we have a group 1 element minus 0 bonds minus 2 unshared electrons. That's equal to -1. And that's where that -1 charge comes from in the hydride. Now, what's nice about hydride is that when it serves as a base, and it's a very strong base thermodynamically, because what we, or I should be careful. It's a strong base. It will readily deprotonate water, and that's what strong base means. But it's also a useful base, I'll say it that way. So if we have like an acidic hydrogen, whoops, I got that dipole labels flipped around. Hydrogen's typically a delta plus, right, when it's attached to things. And so that aren't carbon. So we'll call this the acidic hydrogen atom. Now what I'm getting at is that when the H- reacts with the delta positive on the acidic hydrogen, pushing the electrons onto whatever that hydrogen was attached to, what we get is H2. H2 plus a minus. Now, the nice thing about H2 is that it floats away. This is our Hindenburg gas, so it is flammable. We have to be wary of that. But in terms of thermodynamics, what we should recognize is that since it's a gas, this will float away or evaporate away. This leads to irreversible, for the most, I mean, in a practical sense, this is irreversible deprotonation. The reason why is because the hydrogen gas, while it's inherently not acidic, so you're not really going to see A minus be able to deprotonate H2 gas. That's one reason why this is irreversible. The other reason why is the H2 just sort of floats away and it's no longer present in the reaction mixture. And so you cannot go backwards, which is nice because most acid-base reactions exist in equilibrium and therefore are reversible. Oops, maybe went a little too far there. So that's another example of a base. The amide bases we'll consider next. Now, amide's sort of a weird word because, well, amide sounds like the functional group and spelled the exact way, and depending on where you're at in the world, pronounced the same way. In this context, this also is a nitrogen anion. And so the examples that we see are, the most prominent one is LDA, and this is lithium diisopropyl amide. There's probably some covalent character to this bond. So I'll draw a covalent bond between nitrogen and lithium. As I said, lithium diisopropyl amide. Okay, so that's lithium diisopropyl amide. You could think about it as two lone pairs on the nitrogen. So we have a negative charge on that nitrogen that's formal charge that's countered by the lithium cation. And then other examples are the metal HMDS bases. And so this is hexamethyl disillyl, one word, amide. So there's our amide. So hexamethyl disillyl. And then we have some sort of metal. Now, the basic framework of this is that you have nitrogen attached to two trimethyl silyl groups. So it looks like the diisopropyl, except we have silicon present now. And then when we have this adducted to a metal, now the metal could be any of the lithium, sodium, potassium, any of those three for the most part. And so what you will see is that this will behave much like the example up above. We have silicon now instead of the isopropyl groups, but the nitrogen is still negatively charged with two lone pairs of electrons. Like I said, it could be countered by any of those bases. Okay, so these are kind of interesting and unusual. What we can make note of here is that the pKa is actually quite impressive for these. So the pKa, and let's ask this question, how basic are amide bases? Okay, well, to figure out how basic, basically this and this are, we don't use things like pKb tables. Instead, we use pKa tables, and we show that between, if we look at the pKa of the conjugate acid, which is what we want to do, we say that for diisopropyl amine, it's about 36. And my notes say that's in THF as the solvent. So what that's saying is that the corresponding conjugate base will be quite basic because 36 is a fairly high pKa. That is, this amine, diisopropyl amine, is not willing to give up its hydrogen, which means its conjugate base, the anion, the amide, is desperate to pick up a hydrogen. We could do the exact same analysis using hexamethyl disilyllamine as opposed to the amide base. Its pKa is shifted a bit. Its pKa is 26. So it's less desperate to hold on to that hydrogen, and therefore the conjugate base is less desperate to pick up a hydrogen, so it's less basic. Okay. The reason why we choose these two bases in particular is because they have added steric hindrance, and so they're also not good nucleophiles. So the steric hindrance of the isopropyl and SiCH3, which is a TMS group, trimethylsilyl, prevents most nucleophilic reactions. So these things won't serve as nucleophiles despite having a negatively charged atom because of steric hindrance. Now that's helpful because we want them to deprotonate and remove hydrogen atoms. Hydrogens are just single subatomic particles, so if you have a lot of steric hindrance, you can typically still reach the hydrogen atom. But this is helpful. We call these then non-nucleophilic strong bases. But amide bases in general can be quite nucleophilic. For example, NaNH2, which is sodium amide. Okay, there's nothing attached to the nitrogen that's mostly negatively charged. Is a strong base and good nucleophile. I've never done this reaction, or I've never used this reagent in a reaction, but it does a pretty cool reaction with pyridine. And the reaction has a name that is a favorite amongst my former students, and that's the Chichi-Babin reaction. In the Chichi-Babin reaction, what you do is you take sodium amide plus pyridine. I'm going to draw the double bonds configured this way in my pyridine. It really doesn't matter, but it'll help if we propose a mechanism. But what happens is in this reaction, we're going to see the NH2 actually add to the ortho position of the pyridine to make a 2-aminopyridine. This is a useful reaction because 2-aminopyridines are otherwise harder to come by, whereas pyridine is readily available. The mechanism for this is quite unusual, but the reaction seems to work well. And that is, we consider the nitrogen of the amide to be negatively charged in a nucleophile. And that will add to the pi bond actually closest to the nitrogen. So either one of the ortho positions could participate in this reaction. It's just a resonance structure. We're going to add to the ortho position. Now, whenever you add to an aromatic ring, you have to consider that there's still a hydrogen left over. And so what happens here is the negative charge pushes off the hydrogen, which will be lost as H minus. So quite unusual. Always been interested in this mechanism in more detail, but that's as far as I know it. But anyway, Chichi-Babin reaction. It's always kind of nice to throw in new reactions in the midst of kind of learning some topics. So let's continue onward with the next class of bases. Now, these next bases are both the probably most popular among pure synthetic organic chemists. So people that do synthesis of organic molecules all day in a pure sense, I mean, kind of using petroleum derived chemicals. We hope we're quite dependent upon this class of bases, but these are called the organolithiums. There are several issues with this. The fact that they're solely petroleum derived isn't even the worst of the issues. These are very pyrophoric. So we'll get into that in a second, but here we have a carbon lithium bond. Which is highly basic. Okay, so let's start by looking at some examples of these. The most prominent one is are the butyl lithiums. So there's this one, for example, 4 carbons attached to lithium. There's this one, and then this one. Now, to tell the difference between all of these, we just name them. And for the first one, we call this N-butyl lithium. N referring to normal butyl as opposed to an isobutyl. Second one is called sec-butyl lithium. Okay, we have a methyl group that's a secondary carbon, and so that's where we get the sec-butyl isomer. And then the last one is T-butyl lithium. I believe we abbreviate this as S-butyl lithium, but I've never really seen too many people actually do that. But T-butyl lithium, this is what you would abbreviate it as, and then you could call it tert-butyl lithium. So we have normal butyl, we have sec-butyl, and we have tert-butyl lithium. Now, what's helpful about these is once you have access to them, the pKa that you have to consider is an alkane. Okay, so this pKa of this hydrogen is about 50-ish. So I think that's 53 or 51, excuse me, about 50. Okay, 50, excuse me, sorry. So 50 for this one. Sec-butyl, I've got a pKa of 51. And then for T-butane, I've got a pKa of equal to 53. So the point is the pKa's being up in the 50s for the conjugate base. I mean, these are not giving up a hydrogen for anything. So very basic. Now, the issue with the butyl lithium bases is they're also nucleophilic. Not so much the tert-butyl, but N-butyl lithium in particular. So N-butyl lithium is fairly nucleophilic. So if you can get away with just using N-butyl lithium straight, go for it. But a lot of times this is used as a precursor to LDA. So what you do if you want to actually get your hands on LDA, lithium diisopropyl amide, which is a very popular base, what you do is you start by mixing N-butyl lithium with diisopropyl amide, pKa is equal to 36. So between butane and diisopropylamine, butane is going to take the hydrogen with a pKa of 50. So the equilibrium is going to be non-existent in the reverse direction to form the deprotonated amide base and butane. A lot of times the butane can just go away. But what's great about this reaction is it means that you don't have to store LDA which could be problematic. It sort of reacts with carbon dioxide and that sort of thing. So does N-butyl lithium. N-butyl lithium is not great for even more reasons. But the additional thing to keep in mind is the byproduct is inert, and that's the butane. If you have some butane floating around in your reaction, it won't do anything for the most. I mean, I can't think of an example where it has done something. Okay, so I said this is a nice starting place. I also kind of alluded to the fact that butane is not willing to give up its hydrogen. I would probably cross out the equilibrium arrow in the first place and say, you're not going to go backwards. You're not going to take N-butyl lithium and deprotonate it. So how do you make N-butyl lithium? And this applies to any organolithium. We're actually going to talk about this in more detail in the following lecture, but I'll just mention it now. If you recall, when you have a Grignard reaction, what we would do is we would start with a haloalkane and add a metal to it, and the metal would replace the halogen atom. The same thing happens here. We're going to use lithium 0 and watch it spontaneously replace the halogen of N-butyl lithium to give rise to this. Now, what's interesting about it is you get as byproducts, you get lithium plus Br minus as a byproduct for this reaction. And it has kind of a cumbersome mechanism, but the lithium bromide is insoluble. And because the carbon lithium bond is so covalent, has so much covalent character despite being pretty ionic in nature, because it's so covalent, you actually see that the organolithium is going to be soluble in organic solvents, and typically people use super nonpolar solvents like hexanes to store these things. Now the mechanism is pretty funky. So mechanism for this above reaction is pretty wild. What likely happens is some radical chemistry where you have this starting material and you add lithium 0 to it. So lithium 0 is going to have 1 electron. And then what you do is you do a single electron transfer, which is called SET. Now, single electron transfer, it's not super productive to talk about pushing electrons, but the lithium is going to lose its electron. And the bromine is likely going to pick up an electron, but it's going to be lost as, I drew lithium with an electron. It's supposed to lose that electron, become positively charged. Okay. And then what happens is that perhaps the new radical, the new electron, it got transferred from lithium. I'm going to color that blue. Perhaps it goes on to the butane chain to make the bromine atom, and then the bromine atom ejects 2 electrons to make our carbon chain now possess an anion, in which case we could just let these 2 things combine, or we could see SET, where the lithium does give up its electron, but now the carbon chain has a radical, and the bromine atom is now negatively charged, and then this can adduct with another lithium 0. I'd probably favor the former. So what you would do is you'd punch an electron into the bromine. The bromine would now have too many electrons, and it would undergo homolysis with the carbon-bromine bond, which is a pretty spontaneous process to release a carbon radical along with Br minus and Li plus, which could then drop out as lithium bromide salts. Okay, so that's an approach. It's not something I'd worry about too much. We're going to talk about this reaction a bit more, looking at magnesium and the Grignard reaction in the next maybe 2 lectures from now, I'm not sure. But let's end this one by talking about the biggest drawback of organolithiums, and that is that organolithiums are pyrophoric. And what that means is they will detonate, and detonate is as scary as it sounds. upon exposure to moisture in the air. Okay. There's a really, in this, so what this means is that if you expose these things, and this is true actually for many main group or organometallic reagents, if you expose them to atmosphere, the moisture in the atmosphere will encourage detonation. You'll see flames, you'll see some scary stuff happen. It's overall just scary. It's very unsafe to handle these things out in the atmosphere. So what we try to do is dissolve these things because many of them have enough covalent character between the carbon and the metal to be soluble. So we dissolve them in some organic solvent. Now, what is unfortunate is there have been several accidents where people have gotten the solution with the organolithium on themselves, on their clothes, and it's started a fire. It started people on fire. So obviously that's problematic for many reasons. Now, there's I guess maybe it's almost a decade ago, there was a tragic incident that happened where an undergraduate at a prominent research institution, and just because this is a public video, I better be careful about some of the details, but you can look this up online, actually it accidentally doused themselves with, I believe it was tert butyl lithium, maybe sec butyl lithium. They're all bad. And they weren't wearing a lab coat and they were by themselves in the lab. And unfortunately, what happened was they were lit on fire, and they were wearing a sweatshirt that was made of synthetic fibers. So instead of burning, the synthetic fibers sort of melted into the person. They died at the hospital that day. And it was just a horrible story because it was an undergraduate student at a prominent research institution that had a graduate program. They were working as an undergraduate researcher in a lab that trains PhD students. The undergraduate researcher probably did not receive sufficient training to be handling the chemical. And honestly, there's little blame that should be made at the actual student. This is not like a bonehead incident. It's just, you got to mix all these chemicals together. It's hard to know all the details. Now, if I could share what I believe sort of happened, it's all very understandable, but the person wanted to retrieve 60 milliliters of the pyrophoric liquid. And so they used, logically, a 60 milliliter syringe. Now, I don't know if you've ever used a syringe before to draw a liquid. So let's assume they used an average needle, like not a super tiny needle that makes this really difficult, like an average needle. So they get as much resistance from the actual diameter of the needle, internal diameter of the needle, as just a typical needle. The issue that you should be aware of when you're handling syringes is that the force of pressure, okay, which is working against you as you draw a syringe, the pressure back to pull back the syringe is equal to force times the cross-sectional area of the syringe. So this is about the diameter of a 1 mil syringe, a 3 mil syringe, a 5 mil syringe, a 10 to 20 mil syringe gets bigger, and then a 60 mil syringe might be this big. Okay, so we have a really big cross-sectional area compared to a small syringe. Now what that means is when you're trying to draw a liquid, you're gonna have to really squeeze and pull, okay? It's not gonna be an easy draw. It's not gonna be like, whoop. And if you're going like this, it's hard to be careful. And if you're going like this and you're not careful and you're trying to fill a 60 mil syringe, that is, its capacity is 60 milliliters. That's a common syringe size. If you're trying to fill that completely full, I mean, I know there's some give, with 60 mils of pyrophoric liquid, the plunger is going to hit the back end and it's easy to pop off, especially if you're going like this, like you're putting all your muscle into it. You know, it's just, I saw when this story happened, there were some interpretations where people said, I can't believe they see what happened was the plunger popped off, the syringe and liquid sprayed all over the person. I can't believe people would interpret this situation and be like, who does that? Who pulls the syringe out? It's like, come on, seriously. If you've ever pulled a 60 mil syringe with water, granted, it's going to have more surface tension than a hexane solution of sec butyl lithium. it's hard. It's really hard. And if you're going like this and you're squeezing, you're using all your muscles to pull back, it's hard to be careful. You add that all on top of the fact that this person hadn't done this before, or doesn't have enough experience to, it's just a sad story. Okay, it's just another example of the chemistry that we're doing is important, and it's powerful, and we can really make an impact. But at the end of the day, these are high energy molecules that are ready to do some serious damage if they're not handled appropriately. So always be aware of the safety risks in the lab, because for lack of a better word, these things aren't like accident proof. Okay. You have to be the one that sort of takes charge and is aware. Okay. Anyway, pep talk over. Great lecture. We'll pick up with elimination reactions in the next one.